Hello, everyone, and welcome back to HDL for Digital System Designs. I'm Dr. Mike Brofchek. Hopefully, you've been building some cool stuff. We're going to finish and round out topic 3 here, procedural combinational logic, by putting it all together. This is actually a revised video for this sequence that hopefully ties things together in a more meaningful way. So what we're going to look at is extending the ALU that we built and showed off a few videos ago, and now putting everything together, looking at our always block sensitivity lists, the if else and case statements, our latch problems, wrapping it up all into one nice bundle. So without any further delay, well, let's dive in. So if you look, every single CPU that you have has an ALU, some arithmetic logic unit. Um, if you look at the RISC-V instruction set architecture, there are at least 10 operations that are defined in that ALU. ARM Cortex-M defines about 20. There are hundreds of operations in the x86 architecture. But no matter which one you look at, the pattern is pretty much the same regardless of the scale. You're going to have some always block that has some sensitivity wildcard list with a case statement inside and opcodes. You can have some default assignments and careful operator selection. Remember, that's where we started this whole discussion about operators and their costs. So don't forget that. The ALU is essentially this combination module. So if you can read it, you can read every data path in every processor. So in this course, we will see the fact that we've already introduced the ALU as a case select demo. We're going to treat today as essentially a composition of everything that we've seen so far. So we're going to talk about vectors and concatenation, the cost of operators, size literals, this always block with a wildcard sensitivity list, case statements, default assignments, all the things. We're going to push this forward. A couple topics from now, topic 7 will wrap up the same data path in a finite state machine control path. Topic 11 will look at pipelining, similar block to this. So it all will come back together, but this is still one of those pivotal moments here. So um, one thing that I want to make sure that you don't misconstrue here, an ALU is not just a case statement on an opcode where you just pick the operator for each branch and you're done. Because hopefully what you are considering is that each of those branches is going to cost a little bit different based off the operators you select. So ultimately, an ALU is a composition of all the combinational techniques that we've talked about so far. Each case branch carries some amount of hardware cost. So if you go back to that day 2 cost table of operations, that'll definitely be in there. So our always block is going to enforce the fact that we want zero memory, right? There should be no inferred latches in here. Um, we're going to make sure of that based off how we do it so that we get a clean synthesis run. We don't get any inferred latches. If you do this poorly, right, we could basically get a bottleneck uh, within our decode and execution of our arithmetic logic unit, and that's not what we want. So with that, we're going to add in one of the opcodes that we're going to look at is going to be the shift opcode. And we're going to do a variable shift so you can see what's going to happen. And then we're going to replace it, do some other things so you can look at the hardware impacts, showing you that picking operators really does matter, just like we mentioned earlier, it would. So first up, how about an ALU, a very simple ALU, where I've basically tried to take everything we've seen in the past, a lot of the techniques, about 6 techniques or so, from the past couple days, past couple videos, all in one space. And so I'll talk through them, but if you want to try, you're welcome to pause to see what you detect here. First off, at the top of our always block, what do we have? We have 2 defaults that are set. Why? So that we can guarantee that we're not going to create a latch on a carry or result. All right, so that's right up front. We have defaults set to 0 for both of those. Um, all right, next, we have both carry and result that are concatenations, right? You can see that. on these two lines here, right here for essentially our add and subtract. They are both concatenations, carry and result concatenated together. And what does it equal? It is equal to the sum or the subtraction here. So one very clever way of using that. We are also getting um, out of this handful of other things. We are looking at um, the difference here between uh, uh, basically an or, and down here, um, yeah, I think that that's quite a bit. We have a default case also, which is something else we talked about in case statements. So a handful of elements here, all wrapped into one. And then we also, by the way, have at the very end here an additional assign that does exist outside of our always block, just to show you that that is also possible. All right, so together, um, adding in XOR and shift. So I've added both of those in. See if you agree with how I've done it. What do you think these are going to cost us? So again, I've got an add, a subtract, an and, or, XOR, and a shift by a flexible amount, shift amount. So predict what you think this is going to cost us. Um, all right. So prediction before we actually measure it. We expect that the XOR will probably add about 4 LUTs or so. There's no carry. The variable shift should also add about 4-bit barrel shift adder, 3 layers or so, probably somewhere in the order of 12 to 16 LUTs, right? So that's roughly a guess. Plus our case statement now has select one of 6 instead of one of 4, right? We have more opcodes. So that's also going to add something. So I predict roughly that the addition of 2 additional opcodes, as well as the barrel shifter and the XOR, probably going to add in another 50 LUTs and about 8 additional carries. Well, not additional carries, 8 carries for the 2 adders that we have, the add and then the subtract, which behind the scenes is an adder as well. So our original baseline was probably about 25 LUTs and 8 carries, predicting about a doubling of that to 50 LUTs and 8 carries with the addition of 2 additional operators. So before we go too far, imagine that we have this decode here. Um, Essentially, we have, it looks like, a handful of defined opcodes that translate to plus, addition, subtraction, and or, as well as it looks like for opcode 100, an XOR and a carry bit set. Um, so what do you think? We're going to have basically claiming there's 2 inferred latches. What are they and why? Why do you think that's going to happen? I'll give you a moment. And all right, so bug number 1, there is no default branch. So we've got opcodes 101 through 111. So that's 5, 6, 7, and 8. All basically leave the result, O result, unassigned. So we're going to get a latch on O result for sure. Second bug, O carry only gets assigned in one of the branches. It only gets assigned in the 100 branch. So we're going to get a latch there too. Carry is going to be latched for every other opcode that exists. So the fixes here, you could do a default assign on both signals at the very top before you enter the case statement. And you need to add in a default branch as well within the case statement. Doing both of these is going to fix both of those problems. Okay, so let's take a quick look at a live demo here. And this demo exists in lecture examples week 1, day 3, S4 example 5. So within this space, what we should find is we're going to have an ALU 4 bits as well as an extended version. So let's take a look first. Let's do a quick nano at ALU 4-bit.v just to see what it is. And we'll see that it does have 4 operands. It is and, subtract, add, subtract, and an OR. And so when we look at it, you'll see that we have our carry, result, and 4 opcodes, default, all the things. This matches exactly what we showed earlier. And we can make stat baseline just to see what that is going to take. So we can see the requirements for this. And we see here that we have 8 carry bits. That's 4 for the adder, 4 for the subtraction, and 25 LUTs for all the rest of the other logic. So that's pretty close to what we predicted. Now let's take a look at the other one. Let's look at the extended version of this. ALU, so ALU 4-bit extended version. So in the 4-bit version, we now have 6 opcodes. We have add, subtract, and, or, XOR, and shift left. So what we can see in our actual examples down here, same structure, right? We are not doing any, we're doing this well. There's no inferred latches here. Carry and result both set to default. We now have 3 bits required for our opcode. You can see that we are doing add, subtraction, right? Going to require a carry chain. We have and, or, XOR, and the shift left. Now notice this shift is by some amount that is passed in, right? So that's the case there. We have a default, round things out. Let's see the cost of this. So let's do a make stat extended version. And we notice roughly doubling, not exactly, but 43 LUTs required. No change to the carry. We didn't change those. So essentially the addition of our barrel shift as well as that XOR roughly doubled the cost. Not exactly, but added at least just about 20 LUTs just for those 2 operations. So the question is, you know, how much did that barrel shifter really add? So something you could consider doing is you could do a little experiment and edit it. So why don't we edit our ALU 4-bit extended version, and instead of shifting by a specified amount, by the way, I'm going to not change too much of the code, so I do know that that is going to cause some other issues, but let's just shift this by a constant number. Let's shift this by, let's just say, let's do 2 bits. Let's just make it a, it's just static shift of by 2. Um, and let's just see what happens here. I am going to again make stat extended version. And what do we see here? That our LUTs dropped to 36. So we went from, was uh, 43, and we're down to 36. So that basically means that that barrel shift adder added in roughly 7 extra LUTs to do that barrel shift adder that was unspecified. So again, pretty significant impact of just one one particular operation on our total here. So with that, I think that provides at least some context of putting it all together. To see that, you know, what you put in does make a difference, right? You're generating real hardware behind the scenes. Um, Notice that our carry count didn't change. The new opcodes don't have any carries, the 2 that we added. There was a delta, a change in the LUTs. Uh, the variable shifter did add quite a bit, and our mux, being a little bit wider, has also added in a bit of extra work. Um, so we did try that. We tried to change to a constant shift. I didn't clean up everything, which also could account for a little bit of extra hardware. But in general, you get the idea that what you select, your combinational logic, the operators you select have real hardware costs. All right. So, um, roughly what did we build? Looking at the ALU 4-bit version, we basically had 4 opcodes, about 25 LUTs, 8 carries. Um, the extended version with XOR yielded about 29 gates, a little bit more than that. No change in the carries. Using actually, we didn't quite do that one. We didn't strip it out completely. We did the last version, shift of 2. And so quite a bit of savings. And our most expensive one was obviously XOR plus the left shift by an unknown amount, so resulting in a barrel shifter. So all this to say, our adders, right? And when we say adders, that is add and subtract. Those are going to dominate the carries. The requirement of the carries for both of those is there. Our variable shifter dominates LUTs roughly versus a constant shift. And, if you can, swap out variable shifts for constant shifts, you are going to get quite a bit of savings. Make sure that your branches, right, when you look at this, the branches that you choose determine your total amount of chip area, and that is a line by line choice. All right, so something you could check if you wanted to. What happens when you bump your operands from 4 to 16 bits? What should happen? Well, it should be a linear change for your carries, right? Variables shift in the size of your barrel shifter. It should, in theory, grow about n log n in terms of muxes. So, um, you know, if you can look at the growth rate as you go from 4 to 16 bits, and if you want to do it, maybe go 4 bits, which we have, go to 8, then 16, plot it, see what the change is, and predict what it looks like for 32-bit operands, see what will happen. Can you fit it on our device? So something you should do, check the machine as always. Extend this 4-bit ALU with multiply opcodes, estimate the LUT cost on ICE device, and warn me about any latch risks. So you could ask it this. You could predict what will happen on a 4x4 multiply. It's going to say that it might require about 30 to 40 LUTs. The latch risk if it forgets to have a default for O carry or any of the others. Look at the results. Is this actually what the AI says? A strong AI probably defaults all outputs and estimates to essentially 2x growth. Weak AI is going to omit the defaults and will yield latch. Ultimately, no matter what you get out of an AI system, verify with makestat, right? AI is going to do a pretty good job at the ordering, but the absolute counts are likely to be off. So, big takeaways. The ALU is a great composition of everything we've seen so far. Vectors, size literals, using the always with a wildcard sensitivity list, the case statement, defaults, initializations, operator costs, all of it is in the ALU. So take some time, especially with the lab that's associated with this video series. Do the lab. You will learn a lot, and you will learn by doing. Every case branch carries some hardware price tag, right? Go back to that cost table earlier to get a sense. But again, trust what you get with Yos's stat to see the actual costs. Make sure you've got default assigns at the top of every always. Include default catches for your case statements. You'll notice that we prevented 2 latches in this particular instance. You can predict your gate costs from source, verify them with makestat. Read your code, look at it, see the gates that are actually generated, modify, iterate. It will help. Again, combinational design is a lot of the vocabulary that you've already learned. We've deliberately put it all together. Now you can read RTL, start to read it like a senior engineer, which is, again, focusing on the costs of what you are writing, right? You're not writing software, you are instantiating and creating hardware. So the more you can get into that habit of these lines of code translate to real hardware, the better. All right, so let's do a quick check before class. So why do you have to use essentially a wildcard sensitivity list instead of a manual sensitivity list? And what causes unintentional latches? So number one, manual lists huge risk that you're going to get a simulation synthesis mismatch. When you use the wildcard sensitivity list, you are automatically including all the signals that are inside that block. And so there is no question. What causes unintentional latches? Well, not assigning a signal in every possible path through your always wildcard sensitivity list. So if you have something that isn't covered, right, you've got a path you haven't described or defined, you are at risk of creating a latch, an inferred latch. All right, so name 3 techniques to prevent this latch inference. And adding a variable shift op to a 4-bit ALU, why does the LUT count jump, but the carry count stay the same? So first one, 3 quick ways. Adding default assignments on top. 2, making sure you have complete if-else chains. And 3, adding in a default in every case statement you write. Non-negotiable. So question 4, the adding a variable shift op. Why does the LUT count jump, but the carry count stay the same? Well, your variable shift synthesizes into a barrel shifter. So you basically get a set of 2-to-1 muxes that are going to stack together to create essentially this large structure that is at the base level, roughly n, n log n is going to be the size of this thing. And so there's only LUTs, there's no carry propagation. Basically, this thing keeps reducing, but basically the only thing that you end up adding is LUTs. The only things that really add in to your carry chain are adders in general, where you're cascading information that could overflow. Same thing with multiplies as well, but yeah. So next up, we're going to start talking about sequential logic. So we'll look at clocks, flip-flops, first blinking LED. So basically what we've covered so far is all of the combinational logic, logic with no memory. We looked at the ALU and how everything evaluates at the same time. Um, so we'll build in the next topic we're going to build up to includes time now. So time will now start to allow us to do things with flip-flops, clocks, sequential designs. And so we'll meet a second assignment operator that looks a lot like our traditional assignment operator, and we'll talk about how it differs with the one you've already seen. And so with that, keep building awesome things, and we'll see you next time.